Hello everyone, I am Jia Li. I'm glad to present our co-authors for presenting our work. 3D semantic segmentation task aims to predict a semantic class for each LiDAR point in the point cloud. Although using the multimodality of LiDAR point cloud and camera imagery is conceptually superior, the development of multi-modal segmentation model is still difficult and lags behind the LiDAR-only method. However, we achieved the technical difficulties and proposed a top-performing multi-modal 3D semantic segmentation method termed MSeg3D. We now introduce the challenges and what we do. First, heterogeneous point cloud and imagery are developed with different feature extraction networks. Thereby, we design MSeg3D with jointly optimized intra-modal feature extraction and inter-modal feature fusion. Second, the limited sensor FOV intersection results in that some points outside the camera image boundary have no image features, due to the feature gaps between points inside and outside. The previous multimodal method only focuses on the intersected areas and ignores the segmentation of points outside. To overcome the disregarded multimodal feature learning outside FOV intersection, we propose a cross-modal feature compilation and a semantic-based feature fusion phase to collaborate with the geometry-based feature fusion phase. Finally, under the constraint of model alignment or 2D representation of point cloud, the existing multimodal segmentation works discard many critical point cloud augmentation transformations. Thus, we propose the asymmetric multimodal data augmentation, which enables asymmetric transformations in the LiDAR camera worlds and local cameras for enriching training samples. As shown in the lower right figure, each proposed component not only contributes to the performance improvements on all points and points inside, but also reduces the performance gaps between all points and points inside. The overview presents the architecture details of MSeg3D. The basic GF phase views the pointwise LiDAR features and pointwise camera features, which appeared by geometric association with the sensor calibration. Afterwards, the SF phase further improves the semantic features of all points. Specifically, the LiDAR SFAM and the camera SFAM aggregate the vox features and image feature maps as two short sequences of LiDAR semantic embeddings and camera semantic embeddings, respectively. As shown on the right, the GF phase output features capture the typical and global semantic abstractions by attending to the LiDAR and camera semantic embeddings, with multi-head self-attention and multi-head cross-attention. The SSFM output features will be sent to the point segmentation head. Besides, the cross-modal feature compilation module predicts the pointwise pseudo camera features for the points outside, which knows from the correctly paired cross-modal feature relationships. Moreover, the asymmetric multi-modal data augmentation pre-associates the point coordinates and the pixel coordinates, then augments the point cloud and images with different and arbitrary transformations in Table 1. Note that the pointwise pixel coordinates are synchronously transformed with the image. Through the cooperation of the above components, our method achieves state-of-the-art performance on nuScenes, Waymo, and SemanticKITTI datasets. Besides, the robustness analysis on malfunctioning multicamera input and multi-frame densified point cloud input validates the robustness of our method. This is the end of our representation. You can find more details from our paper and code. Thank you for listening.